All right, so we are looking at fixed axis rotation. We are looking at fixed axis rotation, and like I said, what we're looking at is an object like this. So imagine a CD that's rotating like that, and there is the axis of rotation. Okay, so that's the object you want to have in mind. That's the picture you want to have in mind. Okay, so we will define rotational variables, angular quantities and vectors. So angular displacement, angular velocity, and angular acceleration. We'll look at motion with constant angular acceleration, just like in linear motion. We looked at motion with constant linear acceleration. We'll see how angular and linear quantities are related. As this object is rotating, we'll see how to relate the angular velocity to the linear velocity of this object. This guy is going in a circle. Okay, so we will be looking at angular and linear quantities. We'll define moment of inertia of an object, of a rotating object. Here's the rotating object. We'll define its moment of inertia. Moment of inertia plays the role of mass in the role of mass in linear motion is played by moment of inertia in rotational motion. And just like forces cause acceleration, torques cause angular acceleration. All right. So and that's what we'll be looking at. So here's an object that you want to keep in mind. There's this object that's rotating about this axis. The axis is coming out of the plane of the paper. And you see the problem in this with objects rotating is that every point is going at different speeds. This point is going much slower than this because this guy has to go in a bigger circle in the same amount of time that this guy goes in a smaller circle. So the further away you are from the axis of rotation, the faster you're moving. Okay. So you're going in a bigger and bigger circle in the same amount of time. But what is same is the angle through which each object rotates is the same for every point. Okay, so that's the variable we'll use. So again, like I said, the motion has this object cannot be treated as a particle. It's an extended object. Okay. And I urge you guys to go see these two simulations. Okay. Okay, so here's our object that is rotating. There's the reference line. And you mark a line on the object to measure the angular displacement from the reference line. So here's this object that's rotating about this axis. There's the reference line. And right now, the angular position of this object, this theta is theta. That's the angular position of this object with respect to this reference line. And what we'll be interested in is, and this angular position theta is this linear distance s divided by r. Okay, so theta is in radians. Okay, so when we want to describe the motion of this object, what we'll be interested in is what is theta as a function of time. And that's what I was starting to do, 5t squared. So here's an example. Okay, so the angular position of this object theta with as a function of time is what we're interested in. So if somebody gave you this function, they have completely described the motion of this object. Okay, and just like before, you will learn angular velocity is angular velocity is equal to d theta by dt. So in this case, it will be 10t plus 3. And angular acceleration denoted by alpha is d omega by dt, which is 10 in this case, so 10 radians per second squared. Again, those will be the units. Anyway, so that's where we are headed. Okay. So the angular position of this object with reference to as a function of time is what we'll be interested in. Okay. Okay, so one of the first things we want to define is angular displacement. So imagine that CD in the background. There is the initial position of the CD, and there's the final angular position of the CD. So the CD has rotated through this angle, essentially. Okay. And the angular displacement is the final angular position minus the initial angular position. Okay, like we were saying, this is okay. So we have a question. Can you use polar coordinates to describe the motion of the object? Yes. So polar coordinates are the most convenient coordinates to use to describe this, and that's what essentially we are doing without saying so. Okay. So so again, that's a general theme in physics. What you want to do is for describing different problems, you use different coordinate systems to solve, to describe those systems. So when you deal with gravity, you have to use spherical polar coordinates. So here's a rotation about fixed axis. For this, polar coordinates are used, two-dimensional polar coordinates. And so, of course, for linear motion, the Cartesian coordinates were convenient. Okay, so good question there. All right, so as we were saying, this formula is the same as in the linear displacement case. This was the formula for the displacement, and so now for angular displacement, we have a very similar formula, theta final minus theta initial. And of course, theta final just means theta at t final minus theta at t initial. Okay. So here was the angular position at this time, and there is the angular position at this time. Okay. All right, so let's erase that. Okay. So, and in the linear motion case, we had defined the average angular average velocity. Average velocity is displacement, linear displacement over the time over which this happened. And so we define just like that, angular velocity, average angular velocity. Angular velocity is denoted by omega, and that's angular displacement divided by time. And of course, we are interested in instantaneous angular velocity, which is the limit of average velocity in the limit delta t going to 0, and that's given as the derivative. Time derivative of the position as a function of time. Okay, so going back, so let's see. All right, so let's do this example. Okay, so here's this object you want to keep in mind. This object, its angular position. This angular position is given with reference to this reference line. This object is rotating like so. And what we are interested in, as that object rotates, the description of this motion. This motion is described by giving theta as a function of time. So this is the reference line, and this is the marker on the object. Okay. So if you give theta as a function of time, now I'll make up some function. 7t cubed plus 3t squared plus 5t plus 11. Okay, so now given this function, you have described this motion completely. Okay, so given this function, just like before, given this function, you can calculate the angular velocity. The angular velocity denoted by omega as a function of time is d theta by dt, which is 21t squared plus 6t plus 5. And angular acceleration denoted by alpha is d omega by dt, which in this case is 42t plus 6. Okay, so again, what you're interested in, describing this rotational motion about that axis. The axis is fixed, and when you're asked to describe a motion, what you're asked is for this function of time. Okay, do you guys have any questions on this before I erase this? Okay, and I'm also going to pause and stop the recording right now and give you guys a chance to